Welcome back. In part 2 of our lecture on the physics of the early universe, we're going to continue our exploration of the evolution of the universe from the earliest times our physics can probe until just a little bit after the first 3 minutes. At subatomic scales, the universe is filled with quantum fluctuations. We like to think of space as smooth and empty, but in reality, quantum mechanics tells us it's anything but. The vacuum may look empty, but it is filled with particles and antiparticles being continually created and destroyed. A couple of particles will pop out of the vacuum and then very quickly annihilate again, vanishing almost as quickly as they appeared. If I were to take a look at the structure of the vacuum at any given instant, I might see one place where some of these fluctuations clump up and another place which is an empty void. Close my eyes and look again, and the configuration will change completely. Averaged over time, these fluctuations are continually coming and going, fluctuating, and moving back and forth. They have to be described statistically, but at any given instant, I can see a lot of structure, but that structure will very quickly erase itself in the random fluctuations of the quantum vacuum. Why does this matter? It matters because of what happens during inflation. Ordinarily, the quantum fluctuations are on subatomic scales, but during inflation, the universe increased its size by a factor of 10 to the 26 in an amazingly short period of time, which would take a quantum fluctuation that started out on atomic scales and blow it up to parsec scales. And so imagine, within less than the blink of an eye, you go from the size of an atom to parsecs, the size of a group of stars. Why does this matter? Because what this does is imagine you're looking at the quantum fluctuation field of the universe just before inflation. You see patterns in the vacuum coming and going, some spots denser, some spots underdense, some spots completely void, but it changes in time. What inflation does is suddenly change that scale from subatomic to parsec scales, but do so in such a way that it, in effect, freezes in the pattern of fluctuations. While on average, if it was left alone, a high spot would become a void. Inflation can freeze in a high spot and freeze in voids. Where do we see this? We see this in the spots on the cosmic microwave background. The high-density spots, the warm spots, and the low-density blue or cool spots are the quantum fluctuations that were blown up in scale by inflation during that brief instant when the universe got bigger by a factor of 10 to the 26. The quantum fluctuations of the universe at that instant got imprinted upon the structure of the universe's field of density. They're very small. They're only a part in 100,000, but that's all it needs. Once the universe cools enough that gravity can take over, these become the seeds from which today's superclusters, clusters, and galaxies formed. And once the galaxies formed, they started forming stars and planets and led to us. What we see imprinted upon the cosmic background radiation is a snapshot of the wild quantum fluctuations of the vacuum in the brief instant just before inflation froze them in. Let's keep going. The Quark Epoch begins when the universe was 10 to the minus 12 seconds old and the temperature is 10 to the 15 degrees Kelvin. This is the time when the Electroweak force splits into the electromagnetic and the weak forces. All four forces from this time forward are now separate as we see them today. After the Quark Epoch, the universe has got gravity, strong force, weak force, and electromagnetic force, all working in their separate manifestations, all working in their particular scales. The universe at this phase is still hot, and matter is now just starting to come into being. The universe is filled with a quark-gluon plasma, and as part of this phase transition is the time when the Higgs boson appears. And this means that all fundamental particles now have the mass that they're going to have moving forward in the history of the universe. The Quark Epoch is the epoch in which particle physics really begins to take form. This is followed by the Hadron Epoch that began when the universe was 10 to the minus 6 seconds old and the temperature was 10 to the 13 degrees Kelvin. This is the point when free quarks form together into hadrons, mostly protons and neutrons. We are now leaving the epoch in which free quarks can exist outside of nucleons. Today, free quarks don't exist at all. They only happen very briefly in high-energy particle accelerators, and quarks are only found bound together into groups of 2 or 3 inside of mesons or hadrons. For example, inside a proton, we have 2 up quarks and a down quark. Inside of a neutron, an up quark and 2 down quarks. This is where the quarks are frozen in. Matter as we understand it now begins to emerge. We begin to recognize the emergence of protons and neutrons, the very matter that we ourselves are made of. It's also during this period that free neutrons form, but they can be stable. The universe is still way too short-lived for them to decay, and there are so many neutrinos around and so many electrons that neutrons, as soon as they decay, can in fact be rebuilt. The Lepton Epoch began when the universe was 1 second old and the temperature dropped to 10 to the 10 degrees Kelvin. We're now down to 10 billion Kelvin. This is the time when the neutrinos decouple from matter and begin to stream freely out into space. Free neutrons are no longer stable during this epoch, and they begin the process of decaying. By the time they reach this phase, the numbers are going to settle down to 1 free neutron for every 5 free protons. The free neutrinos that stream out during this period form a cosmic neutrino background that is predicted but not yet observable. Just like the photons from the Big Bang streamed out into space when the universe became transparent at 38,000 years old, so too when the Lepton Epoch begins at 1 second and the temperature reaches 10 to the 10 degrees Kelvin, the universe becomes opaque to neutrinos, and the neutrino should form a cosmic neutrino background. Neutrinos are very elusive and very difficult to detect, and our technologies are not yet advanced enough to be able to see this cosmic neutrino background. We have an idea of what its properties are, and perhaps in some future day, if we develop a cosmic neutrino detector big enough and sensitive enough, we may be able to see it much in the way we saw the cosmic background radiation. That would be a great breakthrough, because that would give us a direct look at what the universe was like when it was only 1 second old. Our direct view of the universe now is as it was when it was 380,000 years old at the time that the universe became transparent to light. It's during this period, during the Lepton Epoch, that we enter into the Epoch of Nucleosynthesis. It began when the universe is about 3 minutes old and the temperature has dropped to about 1 billion degrees. This is when it is cool enough for stable nuclei to begin to form via fusion. Before this, when the temperature is more like 10 to the 10 degrees Kelvin, the local temperature of the radiation field is of order the binding energy of the nuclei, and so as fast as a nucleus fuses, it's destroyed again. But once the temperature drops to about 1 billion degrees, then fusion can begin. This fusion proceeded from 3 minutes for about 10 to 12 minutes, and when it ended up forming 23% helium and small traces of deuterium and lithium that we see today. This ended after about 12 to 15 minutes because the universe became too cold for further fusion to occur. Fusion would not happen again until the universe was nearly 500 million years old and the first stars formed, at which point fusion occurs in the centers of stars and is primarily proton and helium fusion rather than neutron fusion that occurs. We see the products of this epoch between 3 and 15 minutes today as the products of primordial synthesis. The primordial abundances of helium, deuterium, and lithium are giving us a fleeting glimpse of this area that happened when the universe was only minutes old and 1 billion degrees. Recombination occurs later, 380,000 years after the Big Bang, when the temperature drops below 3,000 degrees Kelvin. We've already been here. This is the time when electrons and nuclei recombine into atoms, and the universe suddenly becomes transparent to light. This light streams out and creates the cosmic background radiation that we see today. And now the early universe has given rise to the visible universe that we can see around us today with our microwave and radio and visible light eyes. We're going to continue our exploration of the evolution of the universe now a bit beyond the first 3 minutes and into what happens in the period following recombination until the first stars form. Between recombination, when the universe was 380,000 years old, and about 500 million years after the Big Bang is what we call the Dark Ages. This is a time before the first stars were able to form. Gas clouds were forming, but gravity had not yet collapsed them to the point that they were dense enough and cold enough to begin the fragmentation and formation of stars. We're not sure exactly when conditions became just right for the formation of the first generation of stars, and indeed, the first generation of stars would have been the population 3 stars, formed from gas that was essentially pure hydrogen and helium in the proportions of about 23% helium and 77% hydrogen, with the bare tracings of deuterium and lithium and some later elements. But when these stars formed, they made the very first metals. We see the first appearance in this epoch of carbon through iron in the universe from the very first generation of stars, massive enough to explode and go supernova, and begin spreading and polluting that gas with the heavy metals that hastens the cooling and hastens the beginning of the star-forming epoch of the universe. This ushers in the current epoch of star formation that we live in nearly 13 billion years later. The Epoch of Star Formation began about 500 million years after the Big Bang and continues into the present day. Large-scale structure is formed by the gravitational growth of those initial cosmic density fluctuations that are faintly visible in the cosmic microwave background. Over time, to the present day, what was a nearly uniform but slightly wiggly field of matter eventually was contracted by the action of gravity, and where gravity was able to gather enough material together, dark matter formed halos into which gas fell. Those gas clouds collapse, fragment, and begin to form stars. The cosmic web is the filamentary network of voids and superclusters we see around us today that is the continuation of this process of the slow formation and collapse of cosmic structure out of the gas and particles and light that emerged from the Big Bang 13.8 billion years ago. The Big Bang model is our explanation for how the universe evolved, but it is not our explanation of its origins. Our physics cannot yet probe earlier than the Planck epoch, when the universe was no more than 10 to the minus 43 seconds old. The current frontier of our knowledge, where beyond that our knowledge of particle physics is limited, can be difficult to define, but I'm going to take it as being at the Electroweak epoch, about 10 to the minus 12 seconds into the formation of the universe during the epoch of inflation. We're not really sure the details of how inflation occurred, how fast it occurred, or even how much the universe inflated. The estimates that I gave can only give a range. A 10 to the 26 factor inflation is only an estimate based on our current understanding of the structure of the universe. There are constraints to be read from the structure of the cosmic microwave background and the distribution of matter in the current day. But there are still many questions we need to learn before we can truly say what the details of the universe were like in the instance just following and before the epoch of inflation. Understanding the physics of the universe all the way back to the epoch of quantum physics of gravity is not a physics we can do today, but it will likely be the astrophysics of much of the 21st century and maybe even into the 22nd. We've come a long ways from the beginning, from a bare understanding of the universe where we argued about whether it was the Earth or the Sun that was at the center. And now, just in the first few decades of the 21st century, we know that we live in an expanding universe with an accelerating expansion being powered by dark energy, in which most of the matter in the universe is dark matter, not the material that we're made of. And we can begin to trace the origins of the universe all the way back to 10 to the minus 43 seconds after whatever it was that triggered the Big Bang. What came before? We don't know. What happens in the phases between the Big Bang and inflation? We have a reasonably good idea. What happened after is the universe that we see around us today.